Hello, this is Zhongyu Jiang from University of Washington. I'm going to present our paper, Back to Optimization, Diffusion-based Zero-shot 3D Human Pose Estimation. This paper focuses on providing an optimization-based pipeline for estimating accurate in-the-wild 3D human poses. There are several problems with existing learning-based methods. First, models may suffer from the domain gaps between training sets and test sets. Second, once the model is trained, there is no way to make it better unless the model is retrained. Third, models cannot deal with novel poses easily. Those limitations can be solved by the optimization-based methods by taking advantage of case-by-case optimization pipeline. However, existing optimization methods cannot achieve comparable pose estimation results with learning-based methods. Therefore, by utilizing a diffusion-based pose generation model, we propose the ZeDO, a diffusion-based zero-shot 3D human pose estimation pipeline. Since we are using diffusion models, let's do a quick review. There are two different diffusion processes in the diffusion models: forward diffusion and reverse diffusion. Forward diffusion is aimed at gradually adding noise to the original data until the data becomes standard Gaussian noise. On the other hand, reverse diffusion is to let the diffusion model gradually remove the noise from the input standard Gaussian noise and generate final results. In our case, we train the diffusion model using 3D human pose data. But a diffusion model can only generate random poses instead of doing human pose estimation. Therefore, we add one more term during reverse diffusion sampling. By minimizing the reprojection error, we are able to guide the diffusion model generating the correct human pose estimation results. To minimize the reprojection error, we need to know some additional information like the translation of human poses and camera intrinsic parameters. Let's introduce our pipeline. First, we use an initial pose as our optimization starting point, which is the mean pose from our training data. The initial pose is rotated and used to find the optimal translation as an initial optimization. Then, we are able to take advantage of the PNP algorithm to get translation and iteratively minimize the reprojection error. The optimized poses will be sent to a diffusion model to finish the reverse diffusion sampling, which makes sure the final generated poses are following correct skeleton kinematics. Notice that the diffusion process is truncated, which means the reverse diffusion starts from the intermediate time step since the input poses are noisy poses instead of standard Gaussian noise. Let's dive into the details of each component. First is our initial pose optimization. For any initial pose, P-initial, we try to find the optimal rotation, R0, and translation, T0, which can minimize the reprojection error weighted by the confidence scores of key points. Then, for our iterative optimization block, we are trying to minimize the reprojection error of poses by moving the key points to the projected rays of given 2D key points. For example, here R is the projected ray from 2D key points, and the initial pose, P0, is moving to tilde P0, which makes sure the reprojected key points will match with 2D key points. Finally, the optimized poses are sent to the truncated diffusion model for reverse diffusion, and then the translation is updated by using the PNP algorithm with the newly generated pose. Here, we show the experimental results of our method on 3DPW dataset. As you've seen, we outperform all the state-of-the-art learning-based human pose estimation methods in PA-MPJPE as an optimization method. Meanwhile, our pose generation model doesn't train on 3DPW as well. On the right side, you are able to see how the ZeDO iteratively optimize the human poses and get the final results. Thanks for listening and hope you have a good day.